Good morning to one and all. I am Dr. Jagan Mohan Jannalagadda. So, we are in the 10th lecture of Applied Statistical Methods. So, the code of the course is Ba Zg524. So, before the mid, we have learned testing of hypothesis as well as a regression. So today we are going to discuss simple linear regression and multiple regression again for a different set of models. So what we have learned so far in regression is we started with a simple linear regression model or simple linear regression equation. For that we have done the analysis. After that, we move to multiple regression. So, like for example, if I have only independent variable x and dependent variable y, then the simple linear regression model, what we have considered is, you know very well, that is y equal to beta naught plus beta 1 x plus epsilon, where epsilon is the error random variable follows normal distribution with mean 0 and variance sigma square. But we want an equation for y and x. So that's why we use the notation called simple linear regression equation. So we have taken y here, expectation of y is equal to beta naught plus beta 1 x. But for a big population, it is difficult to calculate the unknowns beta naught and beta 1. So we estimate them with small b naught and small b1 for a given sample of x's and y's. So that's why, so you have estimated 1. So estimated simple linear regression equation as E of y is equal to b naught plus b1 x. So, so this is y crown. So like that, we have done simple linear regression. So for a given set of values x and y, we calculated b0 and b1 because we have formulae for them. After that, we have gone for the analysis of variance for simple linear regression equation and as well as tests of significance for this equation. We have also calculated the coefficient of determination, that is strength of the data, and also the correlation coefficient. So all these analysis we have done for a simple linear regression equation. When there is only one independent variable, we have a simple linear regression equation. But when we have more than one independent variables, we will have a multiple regression. So there, what we started with, we started P independent variables and one dependent variable. So what is the multiple linear regression equation? Is E of y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus and so on plus beta p xp. Here beta naught, beta 1 and so on beta p are unknowns. But for a population, it is difficult to calculate them. That's why we have an estimated one. Like their y crown is equal to b naught plus b1 x1 plus b2 x2 plus and so on bp xp. So for a given sample observations of x1, x2 and so on, xp and y, we will calculate b0, b1 and so on, bp. Actually, we cannot calculate them with a pen and paper or a calculator. We use a software package to calculate them. And also for a given values of x1, x2 and so on, xp, you can estimate y crown. Here you can also calculate the coefficient of determination and adjusted coefficient of determination. That also we have a formula, but the software package gives the values readily. Here also we will have two tests of significance. One is F for overall significance and the other is T for individual, like for B1, B2 and so on, BP, or beta 1, beta 2 and so on, beta. So these things we have already done in the previous classes, and we have also clearly understood how to see the computed table from software and understand the model. Now today anyhow I will repeat a couple of problems of same kind. Meanwhile I'll go to a different generalization to this simple linear regression and multiple linear regression. So generally, now I'm talking about a more generalized linear model in multiple regression. So models in which the parameters beta naught, beta 1 and so on, beta p all have exponents of 1 are called linear models. So the linearity term is depending upon the exponents of beta naught, beta 1 and so on, beta p. If they have powers 1, that model is said to be a linear model. So a general linear model involving p independent variables and a dependent variable, generally we write them as y equal to beta naught plus beta 1 z1 plus beta 2 z2 plus and so on beta p zp plus epsilon. This is a model, a probabilistic model on the lines of a deterministic model. So here Z1, Z2 and so on Zp are independent variables. They are P in number. Y is a dependent variable. Epsilon is the error random variable. Follows normal distribution with mean 0 and variance sigma square. The unknowns are here beta naught, beta 1 and so on beta p. So for a given population you cannot calculate them. So we will take a sample data of Z1, Z2 and so on Zp and Y and will estimate them beta naught, beta 1 and so on beta p. So each of the independent variables Z, now I am concentrating here. I am making it more generalized because just now I have told you y equal to beta naught plus beta 1 x1 plus beta 2 x2 plus and so on beta p xp is a straightforward. Y is dependent, x1, x2 and so on xp are directly independent variables. Now in place of x1 to xp, I am replacing z1 to zp and I am calling them independent variables. But I am making more generalized variable. That's why I am telling you z1 is a function of x1 to xp, z2 is a function of x1 to xp and so on zp is a function of x1 to xp. Then it becomes a more generalized linear model. So if you take the more generalized model y equal to beta naught plus beta 1 z1 plus beta 2 z2 plus and so on beta p zp plus epsilon, we can concentrate on the more simplest one. The more simplest one is what we have discussed, that is a simple linear regression model. So we have only one independent variable x1 and one dependent variable y. So that's why in such a case here what happens, z2, z3 and so on zp becomes 0 and z1 is becoming x1. So this model is called a simple first order model with one predictor, that is the independent variable. Yes, this we have already done. This is the simple linear regression model or a first order model. Now let us move to the non-linear instead of curvilinear. Like suppose, so far we have a first order model, that is beta naught plus beta 1 x. Now we'll go to a second order model. So second order model means we have a power 2 for the independent variables. So what we are taking is, we are taking z1 is x1 and z2 is x2 square. Then what happens? That is known as a second order model with independent variable only x1, but still we are able to construct a second order model with dependent variable y. So that is the beauty here. So what happened here? If you take z1 is x1 and z2 is x2 square, we are able to construct a second order model with one predictor variable. But it can be treated as a multiple linear regression model with x1 is z1 and x1 square is z2. So that's why a second order model with one predictor variable can be treated as a multiple linear regression model. Now, sometimes what happens, we should include the interactions between two independent variables. So that's why if the original data set consists of observations for y and two independent variables x1 and x2, we might develop a second order model with two predictor variables. So even you can complicate your second order model like this: beta naught plus beta 1 x1 plus beta 2 x2, then I'm involving x1 square and writing beta 3 x1 square, then I'm involving x2 square and I'm writing beta 4 x2 square, then after that I'm involving x1 x2, the interaction term, beta 5 x1 x2 plus epsilon. So this is what happened, a second order model, because the highest power is 2. Even if you take the interaction also, the power is 1 plus 1, 2. So it is a more generalized second order model with two independent variables x1 and x2. Though it is a second order model with two independent variables, you can treat it as you can treat it as a multiple linear regression model with x1 is equal to z1, x2 is equal to z2, x1 square is equal to z3, x2 square is equal to z4, and x1 x2 is equal to z5. So what happened? Then we have a multiple linear regression model y equal to beta naught plus beta 1 z1, z1 is x1, beta 2 z2, z2 is x2, beta 3 z3, z3 is x1 square, beta 4 z4, z4 is x2 square, beta 5 z5, z5 is x1 x2. So it can be treated as a multiple linear regression model with 5 independent variables z1 to z5. Right? So in this way, you can write like this. So finally, what happened when the more generalized one I'm writing as, for example, if I take this y equal to beta naught plus beta 1x plus epsilon, we have already done this. because it can be analyzed. Suppose if I take y equal to beta naught plus beta 1 x plus I'm adding one more a second order term, then this can be converted into a linear regression model but in multiple format as y equal to beta naught plus beta 1 z1 plus beta 2 z2. So now what happened? This becomes a multiple linear regression model. Correct. Similarly, if I take if I take y equal to beta naught plus beta 1 x1 plus beta 1 beta 2 x2 plus beta 3 x1 square plus beta 4 x2 square plus beta 5 x1 x2 the interaction term plus epsilon. Then still it can be also written as y equal to beta naught plus beta 1 z1, z1 is x1 plus beta 2 z2, z2 is x2 plus beta 3 z3, z3 is x1 square plus beta 4 z4, z4 is x2 square plus beta 5 z5, z5 is x1 x2 plus epsilon. This is again a multiple linear regression model. So that's why so far what we have understood, earlier we studied a simple linear regression model. After that we studied a multiple linear regression model. Now we are studying a generalized model. Of course, a generalized linear model. So what is a generalized linear model? A generalized linear model is nothing but y equal to beta naught plus beta 1 z1 plus beta 2 z2 plus and so on beta p zp. Observe that beta naught, beta 1 and so on beta p should have powers 1. That's why this is a generalized linear model. So if you take a problem of a simple linear regression model, it can also be treated as a generalized linear model. Similarly, if you take a, there is a one here. If you take a, if you take a second order model also with one independent variable x1, you can treat it as a multiple linear regression model like the way we have done. Similarly, if you take a second order model with two independent variables x1, x2, still it can also be treated as a multiple linear regression model. So that's why the generalized linear model covers all varieties. That's what I want to say. So after a small break, I'll solve a couple of problems in this case. Yeah. So we have understood that we can construct a generalized linear model for a given set of data, right? So using the simple linear regression analysis and multiple linear regression analysis, you can construct a generalized linear model for a given data. For example, let us see an exercise question from our text. So consider the following data for two variables x and y. So x is given and y is given. Develop an estimated regression equation for the data of the form y crown is equal to b naught plus b1x. So this is a simple linear regression equation in the estimated form we are going to calculate. Then use the results from part A to test for a significant relationship between x and y. So we want to find out the tests of significance for relationship between x and y. So we were asked to take alpha is 0.05. Please remember both f test and t test do the same thing for a simple linear regression equation. So we'll do that. So we have x values and y values in we have. So I copied in an Excel sheet, right? So you can do it using a pen and paper for this, but anyhow, it saves the time if you use the direct uh, software, and if you understand the ANOVA table, you can easily write the inference. So maybe from here onwards, I will ask you to study the ANOVA table which will be given in the exams. Based on that, you need to write the inferences. So to avoid calculations continuously. So, so I have copied the data for X and data for Y. Now I want to fit a linear regression model. So what I'm doing is that I'm going to data, I'm selecting data analysis, then I'm going to regression, then I have a regression format, then in which the first one is it is asking y range. So just go to select y column completely. Then you gave y range. Then x range. So go to x range and collect completely. So you got x range. So in your x and y, you inserted labels. So tick labels. So confidence level is in the question 5%. So it's 95%. Then output should come here, and from ninth onwards, I'm doing output ninth. Then OK. So we have the output. So you see the output table, and let us read carefully. So if you see, then we have R square is there. So R square is nothing but what? The coefficient of determination. Means the strength of the data, which means that 63% of data is following our equation. And above R square, we have multiple R. Means which is the coefficient of correlation between X and Y. So these two are important here in simple linear regression analysis table. Then we move to ANOVA table. So for ANOVA table, always you will have three rows. One is regression, second one is residual, and third one is total. So now for regression, only 1 degree of freedom because you have only one independent variable. Total is 5. Why? Because how many observations you selected? 6 for each x and y. So degrees of freedom must be 6 minus 1, 5. Then for residual, the remaining degrees of freedom is 4. Then it's obviously calculating sum of squares for all three, mean sum of squares for the first two, and finally calculating the F statistic as MSR by MSE. Then it is also giving the significance F. So what is there? It is significance F is coming out to be 0.06 around. You know, if that p value is less than or equal to 0.05 as per our alpha, what will say? We reject H naught. But we got 0.0589, which is above 0.05, so we do not reject H naught, which means that the relation is not that much significant. Similarly, we'll go to the next table. So we have an intercept and x, which means that this is B naught and this is B1. Yes or no? Now for B naught we calculated standard error, and for B1 also we calculated standard error. For B naught you calculated T stat, for B1 also you calculated T stat. But we need only T stat for B1. So what is the P value you got? Again it is coming out to be same as P value for F. So again it is not less than or equal to alpha. So we can say that we do not reject H naught. Means the relation is not that much significant. So which means that whatever the relation we are trying to construct for a given data is not significant. Yes or no? So this is what we have. So what is the equation you got? Y crown is equal to minus 6.77. Y crown is equal to minus 6.77 plus 1.23 into x. Is it the same? So we got, what is the equation you got? Y crown is equal to minus 6.77 plus 1.23 into x. Now what else I ask you? The next one is, I am asking you, develop an estimated regression equation for the data of the form. So now instead of a simple linear regression model, I am trying to find out a second order model with one independent variable. That is y crown equal to b naught plus b1x plus b2x square. But we know this generalized linear model can be treated as a multiple regression model. How? How do you do that? So what I am doing is that I'm going to a new page. So the same data I'm copying. I'm pasting here. Right? Now, if you go back to your So what model I am asking you? I am asking you to fit a model of y crown is equal to b naught plus b1 x plus b2 x square. But I am treating it as a multiple linear regression model as y crown is equal to b naught plus b1 z1 plus b2 z2. So finally this model became what? Estimated multiple linear regression model with dependent variable is equal to y and independent variables are z1 that is x and z2 that is x square. So for the software package you need a y column, you need a x that is your z1 and you need a x square that is your z2. Yes sir. So let us go to that one. So we have x means z1. So you need one more independent variable z2 that is x square. So I'm inserting one more. So this is x square. X square I'm inserting. Now how do you get x square? You have to calculate the square of the number. So you can use the format. It is nothing but is equal to this number power 2 square. Enter. So you got how much? 484. If you scroll down, you will get all values. So this is your first independent variable z1. This is your second independent variable z2. And this is your dependent variable. Now let us go to fitting. Data analysis, regression. So input range it is asking for y. So y is this one, right? X range. We have to collect both together for X range. X range is both A and B, right? Then we have to put labels because we selected labels also. Confidence level I'm taking 95% and output range I'm taking at 9. Right? 9. So then let us run it. So output range I'm putting at 9. So we got a output here. Let us study the table clearly. So the first one, because we are treating it as a multiple linear regression model, we will have two coefficient of determinations. One is R square, that is how much? around 95%. So 95% is your coefficient of determination. But for a multiple linear regression model, you will have a adjusted coefficient of determination. So we know the reason behind that. So how much it is? 91%. So what we have found, 91% of the observations fit the equation. If you take these type of model as B0 plus B1x plus B2x, whereas if you go to the previous one, only B0 plus B1x model, the R square is how much? 63% only satisfying the equation, whereas here 91% satisfying the equation, means 91% of the data fits the equation. So isn't it interesting? Because by changing the model slightly, we have found that 91% of the observations are fitting the data straight line. Then we move to the ANOVA table. As usual, ANOVA table will have three rows: regression, residual or error, and total. So regression degrees of freedom is 2. Why? Because it is a multiple linear regression equation, two independent variables z1, z2. So degrees of freedom is 2. For total degrees of freedom is 5 because we have taken 6 observations for each variable. So 6 minus 1 is 5. Then for the error degrees of freedom is 3. So the next column is sum of squares for all 3. Then mean sum of squares for first 2. Then F statistic is MSR by MSE. So how much and what is the significance? 0.013. So what happened? Which is less than or equal to your alpha, because your alpha is how much? 0.05. So which is less than or equal to alpha, less than or equal to alpha. So that's why alpha is 0.05. Yeah, you're right. Strictly less than works here. I understand. I'm just telling you the condition. So that's why what happened? Overall significance is there, which means that this relation is significant. Whereas if you take only B0 plus B1x, then the relation is not significant. But here the relation is significant, which means that this is somewhat the best model than the previous one. This is overall significance. But in multiple linear regression model, individual significance also play a very important role. So now you see the last table, intercept, the coefficient is B0. Is how much? B0 is around minus 168.88 and B1 is 12.19 and B2 is minus 0.18. So these are the three coefficients of the model. Next, the next column is standard error for all the three coefficients. We have a formula for that, long back we discussed. Next, we calculated T statistic for all the three coefficients. But remember, for individual significances, we need tests for only beta 1 and beta 2. Beta 1 and beta 2 means B1 and B2. So for B1, what is the T statistic? It's around 4.58. And for B2, the T statistic is around minus 4.13. Now tell me, this is the P value for B1 or beta 1. How much you got? 0.019586779. Is it less than or equal to your alpha? Yes. That's why the coefficient beta 1 is significant. Similarly, if you go to the coefficient beta 2, it is also less than or equal to 0.05, which means that the coefficient B2 is also, or beta 2 is also significant. So you see now, if you fit a B0 plus B1x model, the coefficient of determination is very less, overall significance is not there, individual significances are also not there. But whereas if we try to fit a model B0 plus B1x plus B2x square, surprisingly coefficient of determination and adjusted coefficient of determination is almost above 90%. Overall significance, yes, significance is there. Individual significances, yes, individual significances are there. So you can say that compared to the previous model, this is a best one. Yes or no? So this is the concept of generalized linear model. So any other queries on this? Then I'll move to a completely nonlinear models now. Any queries? Yeah. So then I'll stop the session here and I'll again start with a nonlinear regression after taking a few minutes break.